is equal to 0.55a. So, but finding the acceleration this time, well, we know the time. Let's find the acceleration going, sort of reversing this process. Any questions on this before I make it go away? Oh, sorry. Yep. All right, this time I know that the distance, or the displacement, is 0.50 meters. I know that the time is 1.28 2871428. Oh, you still have it?
Yeah, that's it.
Okay. Seconds. I don't know the acceleration. I do know my initial velocity to be 0 meters per second. And there we go. Because my initial velocity is 0 and my acceleration is constant, I can use this formula again. 1/2 a squared. I know this is 0.5, and that's equal to 1/2 a times 1.28711428 squared. So if somebody kind enough to square this and then multiply times a half. .828 times a divided by 0.828. And so a becomes whatever that is.
Six point oh
0.6.
6.036.
It's got to be less than 1.
Sorry, I thought that was 5.
No, 0.5. So 0.6. I. That was it?
Yeah.
Okay, units?
Meters per second squared.
All right. We now know the acceleration. We can take that, plug that into here. So we have 0.49 minus the friction is equal to 0.55 times 0.6038. So first off, what is that? I want to get F all by itself, so there are several ways of doing it. I'm just going to add F over here and subtract 0.33209 to the other side. And I end up with 0.49 minus 0.33209 is equal to my friction. Oop, I lost my subscript there. Point 15791.
Yes.
Newtons? Sorry, I meant to say units. Newtons. All right. It is less than the weight, but it is still a positive number, which I would expect given the fact that I subtracted it. And just, I was not planning for the time to be so far off, but since we were there, I thought, hey, let's figure out what the friction is. Questions before I make a couple extra comments?
How would we figure out how much that actually like affected it by?
How much that friction?
That affected the time by?
Well, it should have affected it, since we assumed that this friction was responsible for the difference in time, it would,
But like
realistically, you would run several trials and, because we have that in essence, we had weight minus the friction is equal to that total mass times accelerations. That's in essence what we have over there. If I add friction to the other side, weight is equal to MA mass times acceleration plus the friction, just adding it over. This is just mg. The hanging mass is equal to the total mass times acceleration plus the friction. And if I divide by g, now we'll keep that as is. So if I plotted acceleration versus the hanging weight, basically that's my y and x, that's my slope, and that's my intercept. The friction shouldn't be changing as we go, or not substantially, and so the intercept would be the friction. So you can see how much it affects it by how far off of zero it is. Does that answer your question?
Yeah.
Okay. Couple other points here. One, recognize we did crude estimates of the masses. There was something else that hit me. Oh, the timing. In this particular case, did you time when you saw it hit my hand, or did you anticipate and hit it and stop it when you anticipated it to hit my hand?
I hit it when I hit your hand.
Anticipate.
Get that? And so there's an extra delay there. If you've taken I assume all of you have taken driver's ed. What they talk about is a 3/4 of a second delay when you're braking. I forget, it's been a few decades. But the time you see that the car in front of you has stopped, putting your foot on the brake pedal, there is a time lag there. So the fact that you were all consistent was surprising, because usually there's a much bigger variation, so nice synchronization. So I think there's an issue with timing there, which means that the only way we can reduce that is we either add more mass to the cart, or we have a different method of timing. We will add more mass to the cart, and I think less mass on the end, so it takes more time, so any errors and reflexes would be reflected would get washed out. If it took 5 seconds and everybody was off by 1/4 of a second, it wouldn't have as big an impact. Another way that you can do is you can set up photo gates. I can have a photo gate here and a photo gate there. I get this so that it's not moving before it goes to that first photo gate, so as soon as you remove your finger, it trips the photo gate, and then you just see what time it goes to the second photo gate. You get much better timing that way. But it does rely on its being right there, right before the first photo gate, so that if it just moves slightly, it's going to trip it. That's just making way too much noise. There's an issue there. The third way of time, besides the photo gates and the stopwatch, the third way is to do the LabQuest and look at position versus time. So if I have position versus time, it's probably going to look relatively flat, and then you're gonna get a sharp increase, and then it's gonna hit something. You wanna take a chunk here, where you get this nice smooth curve. If it's not smooth, probably should redo it, clean the track, something like that. So we need to figure out what this equation is of that line. And so you'll go into LabQuest curve fit quadratic. So you do a quadratic curve fit. And you'll get, so your y, it'll be, does y equals ax squared plus bx plus c. I think that's the way it presents it. C is dependent upon where it starts. B depends upon its initial velocity. And there's some caveats in there. I don't expect it to be around 0 unless your timing is perfect, but this is the part I care about here. In the lab, I call this the coefficient of the quadratic term. That's a C there. Of the quadratic term. Its units are meters per second squared. It is not acceleration. It's related to it, but it's not acceleration. So what you're gonna write down is this A value here. This A value is half the acceleration. So you'll do 3 trials or 4 trials, whatever I prescribe. You'll find the average value of A, and then you'll multiply by 2 to get the acceleration. So your acceleration is gonna be 2 times whatever your average A value is. This is, once you understand how to find this number, this is a whole lot simpler than the other 2 techniques. I've done labs with the other 2 techniques. Yeah, there's much less hassle on this one. All right, questions?
What was it called again on the LabQuest quadratic?
It is, you would go to, I think it's analysis, that's gonna be at the top menu, and then curve fit, and then you'll check position, there'll be a checkbox, position, and then you'll choose quadratic. There'll be a drop-down menu. If you're using a LabQuest 2, it starts out with nothing, and you do a drop-down to do quadratic. If you're using a LabQuest 3, I think it automatically comes in with linear, but still do the drop-down to get quadratic. Now, to see if you've done it correctly, when you go, after you've done analysis, curve fit, position, and quadratic comes up, what you would see is this whole thing, but there would be little brackets right there indicating the part that you've highlighted. So you gotta highlight it, and then when you go in there, you should see these 2 black brackets on top of the graph, and that tells you the part that it's gonna map. It's gonna ignore anything outside of that when it comes time to actually coming up with these numbers. So if you go too far one way or the other, if you go too far over here or too far over here, the numbers will seem strange. All right, let's head on down to the other room and show that physics works. This is not change the pace for physics labs.